Hello, good evening, all of you. So today we have to start computer organization and architecture. I hope all of you are doing good. So if we see about the computer organization and architecture, just a minute. This subject is very important for the GATE exam. If you want to secure a very good rank in the, or you can say in the top 100 rank, then this subject is very, very important. You all should have a very clear understanding regarding this subject. Okay, this is a very conceptual subject. When your concepts will be clear, then it will be very easy for all of you to solve each and every question in this subject. Okay, every year many questions come in this subject, and some questions are there that becomes very tricky for all the students to solve. But if you are able to solve those questions, then that questions will definitely help you to get a very good rank. Okay, so, two subjects are very key subjects if you want to hold a very top rank, or you can say a top 100 rank. One is computer networks, and the other is computer organization and architecture. Okay, so this computer organization and architecture, we will complete it in three modules. Okay, we have to complete this complete subject in three modules. In the first module one, it will be we will understand what are the computer functionalities. Computer functionality. In the second module, we will study about the different components of computer components. And in the third module, we will study about data representation. Data representation. Okay, here is specific something like fixed point versus floating point data. Right now, don't think a lot about these keywords. I will explain each and everything very well, clear to all of you. Okay, so we will complete the complete course in these three modules. You can see that topic is computer organization and architecture. That what is the complete architecture of the computer. When you have to go to any memory cell and you have to just read the data, perform some functionality, like you see na, that you write 2 plus 3 in the system and the calculator returns the 5. So how these things, how the computer reads any data from the memory, how it performs that functionality, we will study everything about these things in this subject, computer automation and architecture. Okay, now whatever I will explain, more or less it will be sufficient for the GATE exam. Just follow properly the notes that I am going to give in this complete syllabus. Okay, you have to just blindly properly follow the notes. You have to solve the previous year questions, and also you have to give the mock test for the practice purpose. But sometimes suppose if you feel any doubt in any topic, if you want to know something more, sometimes you feel that you should know that topic only, then you can refer some books. but you have to refer the book only in the case that if you want to understand some specific topic. Otherwise, you don't need to refer any book. Okay, so I'm just mentioning the name of some books that you can refer only when if your concept is not clear regarding some topic. Okay, reference books. I'm mentioning here two books. You can use any of them. One is Computer Organization. It is by William Stallings, and the other is Computer Organization and Architecture by Morris Manor. I am once again saying that for the GATE exam, it is not necessary that you read these two books. Okay, I am just giving the name of the reference books only for that case that if someone is having any doubt or the concept is not clear for any particular topic, then only you have to refer the book. Otherwise, there is no need to refer any book. Okay, I hope it's clear to all of you. So today we will start with some basic keywords, basic things about the computer organization and architecture that we should know before going deep dive into this subject. Okay, first we should know few keywords. So first we today we will start the first module, the computer functionality. In this module we will understand the basic keywords that we require later on in the complete subject. Okay, so this first module is for your concept building, proper concept building, so that you can easily understand this proper subject. Okay, so first write these reference books and these three module links that I have written on the board, and then we will start the first module, computer functionality. I hope all of you have noted down. Now we will start the first module, module 1, and this module is computer functionality. Okay, this is the first module that we have to study. So in this module, we will study various keywords. First, write the heading, keywords. The first keyword, the basic thing in the computer organization, the first word is computer. So what is computer? Now the computer is, you all know that it is a computational machine which is used to process the data under the control of a program. What happens? Let's suppose this is a computer, right? In your computer, you write some program. There are many programs in your computer. Suppose we take a basic example. Suppose we have written a program to add two numbers. So we have written that program into the computer. Now what we have to give? You have to give the two numbers, means you have to give the input. So what happens in the computer? You write the program, you give the input as a data, and then what you get? You get the output data. So you can see in the computer, you give a program, you give the data and input data, and then you get the output data. So computer is just a computational machine where you provide the program, where you give the input, and then you get a output. Okay. So first write the heading computer in the keywords. In the keywords, first write the heading computer, and in the computer write it is a computational machine. It is a computational machine used to process the data. Used to process the data. It is a computational machine used to process the data under the control of a program. Under the control of a program. It is a computational machine used to process the data under the control of a program. Okay, so computer is just a computational machine, right? Which process the data, which process the input data that we give. We give this input data to this computer, it processes this input data through this program, and then it gives the output. So draw this diagram also. We will learn each and every basic concept. What you all have to do is just the hard work. Okay, I will explain each and every concept very well clear to all of you, that you can solve easily any question of the gate exam. I hope all of you have drawn this diagram. Now write the second keyword. The second keyword is program. What is program? So what is program? We see in the program we write a sequence of instructions, right? We write many instructions, and also in program, like you have seen, you declare the variables, like you write like this: int a equals to 2. So you assign the variables also with some data, and there are many instructions that also perform some operations. Like suppose there is a variable b, and you are performing a plus 3. So this is a instruction which is performing some operation, and this is the instruction which has some data. So the program is a sequence of instructions along with our data, right? So write the second keyword program. Write the second keyword program, and in the program write program is a sequence of instructions. Program is a sequence of instructions. Program is a sequence of instructions along with a data. Along with a data. So in the program, what do we have? We have the instructions and we have the data. These two things we have in a program, right? Now what happens whenever you write a program, you just write in a simple way, right? But at the end, with the system, when the computer has to execute this program, it is converted into the binary code, right? In the 0 1, the computer understands only 0 1. So that's why this program is completely converted into binary code, right? So if you write that, what is instruction? Instruction is, it will be some binary code, Instruction is some binary code, right? Bind with Instruction is some binary code bind with operation. Bind with some operation means when you see the instruction, like you can see here in A the 3 has been added. So here operation has been performed, right? And what is data? It is also binary because at the end everything is a binary, right? 0 1. What is data? It is a binary code bind with value, right? In the data, a value will be assigned to some variable. In the instruction, there will be some operation will be performed, and this completely will form the program, right? So now write the next keyword. The next keyword is instruction. First, write this complete diagram about the program, and then write the keyword instruction. Now write about the instruction. It is a binary sequence. It is a binary sequence which is designed. It is a binary sequence which is designed inside the processor. It is a binary sequence which is designed inside the processor to perform some task. It is a binary sequence which is designed inside the processor to perform some task, right? So instruction, it is just a binary sequence. Everything is a binary sequence, 0 or 1, and instruction is just designed so that it can perform some task. Okay. Now write the next keyword, which is data. Now write regarding the data. It is a binary sequence. It is a binary sequence which is associated with a value. It is a binary sequence which is associated with a value based on the data format. It is a binary sequence which is associated with a value which is associated with a value based on the data format. We will see there are various data formats. Like if you have listened some names, like you can represent data in the sign magnitude form, in the ones complement form, twos complement form. There are various ways. So these are the data formats. We will learn about the different data formats later on in the course. So right now, what is data? It is also the binary sequence represented using 0 or 1s, and which is associated with a particular value. Okay. Then next keyword is, just write, it is encoding. Now we have to learn two things. One is encoding and the other is decoding. So for encoding, there is an encoder. Okay, this is the encoder. Now suppose for example, suppose we have four operations, four type of operations. Okay, suppose one is addition. I'm just taking an example. Okay, suppose one is addition, one is subtraction, one is multiplication, and one is division. Suppose addition. Now you have four operations. So four operation can be represented using how many bits? 2 bits. So as you can see, the plus can be represented using 0 0. If you have to represent minus, you can represent using 0, 1. Suppose you have to represent multiply, you can represent using 1, 0. Suppose if you have to represent divide operation, you can represent 1, 1. Now you can see there are 4 operations, right? But for each operation, you can represent it using few bits. So if you give any operation, you will get the corresponding encoded bits. So suppose if there are here you have 4 operations, so you can represent using 2 bits. So similarly, suppose there are n type of signals. There are n type of signals. When they will be given to this encoder, then each signal, the encoder will encode into log n base 2 bits. For example, here like there was 4 operations. Each operations can be represented using log 4 base 2 bits. Log 4 base 2 means using 2 bits. So if there are n signals, the encoder will encode them into log n base 2 bits. These are the n signals. Okay. So just write the heading encoding, draw this diagram, giving n signals as an input to the encoder, and the output will be log n base 2 bits. Now write regarding the encoding. In this process, in this process, in this process, n signals, in this process, n signals are represented with, in this process, n signals are represented with log n base 2 bit format. N signals, small n signals are represented with log n base 2 bit format. It means if you give any signal to this encoder, it can represent that signal in log n base 2 format. Okay. The next thing is decoding. It is completely opposite to the encoding. The encoding is done by the encoder, and decoding is done by the decoder. Right. Now suppose if you will give here n bits, right? Then what happened? With n bits, the number of possible outcomes are, the number of possible signals are 2 to the power n signals, because we have seen that in the encoding with log n base 2 bits, n signals are possible. So the decoder, what it will do, suppose for example, this first output, suppose this is for plus operation. Okay. Second output, for example, suppose I am writing here an example. Suppose we have 4 operations, right? And here n bits have been passed. N bits means 2 bits have been passed. Now suppose 0 0 have been passed. This is output is for plus, this is for minus, this is for multiplication, and the last is for division. Now what will happen? Suppose 0 0 is passed. 0 0 means plus. So what will happen? This first output signal will become 1 and remaining will become 0. It means 0 0 will represent that this is for to activate the operation of addition. If you will pass 0 1, it will say activate the operation of subtraction. If you will pass 1 0, it will say activate the operation of Multiplication. If you will pass 1 1, it will say activate the operation of division. So that's why the decoder is used. Okay, just write the heading decoding, draw this diagram, and now write a line regarding the decoding. In this process, in this process, n bit decoder, n small n bit decoder generates 2 की power n 2 की power n possible output signals. In this process, n bit decoder generates 2 की power n possible output signals. And also draw the diagram that is mentioned on the board. Now if you see that how we write any program, what happens? You write a high level language program. This language could be anyone. Okay, you write a high level language program in any language, C, C++, Java, any language, right? Then it goes to the compiler, and compiler compiles the language. If you have studied the compiler, you know the functionalities of the compiler. It checks various errors also, syntax error, semantics error. It does a lot of things. And after the compilation, this will be converted into a program of low level language, or okay, assembly level language also. Low level language. Now, after that, it is converted into codes. For example, binary codes, or you can say hexadecimal code, or you can say octal codes. It can be converted into anything, right? Now, we have seen that suppose now the program will be converted into binary codes, and each instruction, each line will perform some operation, right? So now we have seen that if we have n signals, then it can be represented using log n base 2 bits, right? So now each instruction, suppose if there are total capital N instructions, right? So they will be converted into log n base 2 bits, right? And then what will happen? It will be passed to the decoder. And what decoder will do? Decoder will be connected. This there will be an hardware. There is a hardware. Now each output of the decoder will be connected to some hardware port. Okay. Now what will happen? Each sequence of bits, each sequence of these bits will represent an operation. Like we have seen here, that suppose 00 will represent plus, 01 minus, 10 multiply, 11 divide. So in the same way, it will be implemented here. This log and base 2 bits will represent some operation, and for that operation, the decoder will just activate that hardware for that instruction. So we have seen that how our language, first you write a high level language program, then it goes to the compiler, and then it converts into the low level language. After that, you convert into the zero and ones. After that, each instruction will be divided into the log and base 2 bits, and then each part will be then decoded into an operation which is associated with a hardware. Okay. Now, if you come in the from the opposite direction, then in the place of decoder, you will have encoder. Whether this complete flow is clear to all of you, that how you write the code and how then it gets implemented on the hardware. You have a high level language program, gets converted into compiler, finally converts into the binary codes, and a particular group of bits, log and base 2 bits, will represent an operation, and with the help of decoder, that operation will become active on the corresponding hardware. Whether this is clear to all of you or anyone has any doubt? I want the response from all of you, that whether it's clear to all of you. If anyone has any doubt, you can ask regarding that. You have to understand properly that how actually you write the code and how actually it gets affected on the hardware. For each operation, there will be some hardware which is performing the action, right? Okay, David, I am clearing once again. I am just saying that suppose you have a program, and in the program you can write only four type of instructions. One is addition. This is just an example, okay? Other is subtraction, multiplication, multiplication. The last is division. Now, to represent these four operations, you require only two bits: 0, 0, 0, 1, 1, 0, 1, 1. Right? You have total here four instructions. But to represent each instruction, how many bits do you require? You require only two bits, right? So that's what I have mentioned here. That suppose if you have total n instruction, that to represent one instruction, you just require log n base 2 bits. For example, here you have four instruction, and for each instruction you require log 4 base 2 equals to 2 bits is required to represent any instruction. Now whether it's clear, David? I hope now it's clear to you, David. So now we will move forward. Okay, very good. So now we will see some structure of the computer, some various structures that we use. So now write the heading computer architecture. Just write the heading computer architecture. Okay. Now we study two types of architectures, and this whenever you do bifurcation, you say that there are two types of architecture, then these two types should be on some basis, on some difference. So it is on the basis of the program storage, that where do you store the program. So on the basis of the program storage, this architecture has been divided into two types. Okay. So this division in the basis of the program storage, that where do you store the program. So one is Van Neumann architecture, von Neumann architecture. Von Neumann architecture. It is also known as single memory architecture. Single memory architecture. Okay. And the second is Harvard architecture. Harvard architecture. This is multi memory architecture. This is multi memory architecture. Right. So the computer architecture is divided into two types. One is von Neumann and the other is Harvard architecture. I will explain both these architectures, what is the difference in between them. But first understand that these two architectures are on the basis of the program storage, that where do you store the program actually, right? If you all know, we have a RAM in our computers, random access memory, and also we have ROM, read only memory, right? In the ROM, we can only read, we can't write, right? It is a read only memory. Now, what happens in the von Neumann architecture? Suppose if you have to execute any program. So now if you have to execute any program, right now don't write anything, okay? Just try to understand what I am saying. So what happens in von Neumann architecture, that suppose whenever you have to execute any user program, then you have to bring that program into the main memory. The main memory is RAM, random access memory, right? And both the instruction and the data, right, is in the RAM only. So whenever you have to execute any program, you have to bring that program into the main memory to execute, so that CPU execute that main memory part of the program, right? But what happens in the Harvard architecture? In the Harvard architecture, instructions and data are stored in separate memories. Separate memory means one is RAM and the other is ROM. So instruction will be stored in the instruction will be stored in read only memory, and the data will be stored in random access memory. So this part will be the where you are storing the instruction, This will become code memory. You are writing the code part, and this is data memory. So here you can see in the von Neumann architecture, both the instructions and the data are in the RAM, random access memory, and the Harvard architecture, the instructions and data are in separate memories. Right now, what happened in the von Neumann architecture? If you want to separate, if you want to execute any program, you have to just bring that program into the main memory and you have to just execute it. What is the use of the Harvard architecture? Suppose you have to design any system for a specific case. For example, you design various microcontrollers, embedded systems. In those cases, you want to perform some specific functionalities. You don't have to change the actual code. You have to change only the input. So you just put that complete code in the ROM, right? Read only memory. And then you have to just give the data, different data. So you just give the data into the data memory. So now the code can't change. It is just read-only memory, and the data will change. So for the embedded systems, for the microcontroller design, you just use the Harvard architecture, right? And for the normal purposes that we use the, for example, the personal computer. The personal computer is based on von Neumann architecture, because in our personal computer, what happens if you want to execute any process or program? That program comes to the main memory, and then then the CPU executes that program. So it is a von Neumann architecture, single memory architecture. But in the Harvard architecture, it is designed for a specific purpose. So that's why all the code and the instruction are stored in the read-only memory so that it can't change, and the different input is given through the random access memory. Right? So there is a data memory and there is a code memory. Okay. So now write the heading computer architecture. Now first write the heading computer architecture. Now write few points. Computer system functionality. Computer system functionality is a program execution. Computer system functionality is a program execution. Full stop. Computer system functionality is a program execution. Full stop. Based on the program storage, based on the program storage, computer architecture is divided into two types. Based on the program storage, based on the program storage, computer architecture is divided into two types. First is first is single memory architecture. I have written on the board. First is single memory architecture, or you can say von Neumann architecture. First is single memory architecture, or you can say von Neumann architecture. The second is multi memory architecture, multi memory architecture, or you can say Harvard architecture. I have written on the board. Okay, Harvard architecture. Okay, now write now write in von Neumann architecture. In von Neumann architecture, user program. In von Neumann architecture, user program is always required. In von Neumann architecture, user program is always required in the main memory. In von Neumann architecture, user program is always required in the main memory. So CPU executes CPU executes the main memory part of the program. So CPU executes the main memory part of the program. The main memory part of the program. Full stop. Here, here ROM acts as a here ROM read-only memory. Here ROM acts as a control system. Here ROM read-only memory acts as a control system. Here read-only memory ROM acts as a control system. Now write this diagram for the von Neumann architecture. The first diagram under the von Neumann. Just write the first diagram under the von Neumann architecture, and after writing that, write the example as personal computer. This architecture is used in personal computer. Example, personal computer. Now write the next point. In a Harvard architecture, in a Harvard architecture, in a Harvard architecture, instructions and data in a Harvard architecture, instructions and data in a Harvard architecture, instructions and data are stored in a Harvard architecture, instructions and data are stored in separate memories. Instructions and data are stored in separate memories. That is that is RAM and ROM respectively. That is RAM and ROM respectively. So CPU always executes. So CPU always executes. So CPU always executes the predefined program. So CPU always executes the predefined program in ROM memory. So CPU always executes the predefined program in ROM, read-only memory. In ROM memory, CPU always executes the predefined program in ROM memory. Just draw this diagram under the Harvard architecture, and its example is embedded systems. So you can see two types of architecture based on the program storage. One is von Neumann, which is also known as single memory architecture. Other is Harvard architecture, which is also known as multi-memory architecture. In von Neumann architecture, whenever you have to execute any program, you have to just bring it into the RAM main memory, and then the CPU will execute it. Both the instructions are data lied in the random access memory. But in the case of Harvard architecture, instruction lies in the ROM, data lies in the RAM, and there is a predefined program that always stored in the RAM ROM in case of Harvard architecture, and you have to just give the input through the RAM. Okay, I hope it's clear. Now write one point. Now write one point. Computer organization. Computer organization is a implementation of the computer organization is a implementation of the von Neumann architecture. Compute, Computer organization is a implementation of the von Neumann architecture. Computer organization is a implementation of the von Neumann architecture. So user program, so user program, so user program always required in the main memory. So user program always required in the main memory. So whatever we are going to study in this computer organization, everything is based will be based on the von Neumann architecture, where the complete program and data complete instructions in both the instruction and data means the complete program will be in the main memory. Okay, whether both the architectures clear to all of you, von Neumann architecture and Harvard architecture. Always remember, sometimes in the GATE exam, they confuse with the word single memory and multi-memory. Von Neumann means single memory architecture because in the RAM only both the instruction and data is present. Harvard architecture, multi-memory because both ROM and RAM has been used. Instruction is in ROM and data is in RAM. That's why Harvard architecture is multi-memory architecture. So whether both the architectures are clear to all of you? I am waiting for the response for all of you so that we can move forward. If anyone has any doubt regarding any of these architectures, you can ask. These are the basics that you all should understand very well. Okay, so I hope now it's clear to all of you. So now we will see the actual memory organization. Okay, that how the memory is actually there and how do we use it. Now write the heading memory organization. right? What happens? This memory is divided into various chips, various cells. What happens? This is a complete memory, and what we do, we divide this memory into various cells. These are the cells. Okay, these are the different cells. Okay, so what happened to these cells? We give a unique number so that we can identify that at which cell we have stored the data. Suppose in the memory we have to store the data at any particular cell, then how to recognize any cell? We will give a unique number, and that unique number will be known as the address of that cell. Okay, and with the help of address of that cell, we will just enable the cell and will read or write at that cell. For example, suppose if you want to access this cell and we can perform either read or write. So with the help of address, we can go to this cell, right? And whether we have to read or write, what we have to do is explained with the help of control signals. The control signals will tell that whether we have to read or write or what we have to do. Read or write. What do we have to do? Okay. So in the we can see the memory organization has been completely divided into various cells. Each cell has a unique number associated with it, which is known as the address, and that address enable the cell. And when that cell will be enabled, then only you can read or write from that cell. And how to know that whether you have to read or write? With the help of control signals. So what CPU will generate? CPU will generate an address and will also give a control signal. So what you have to do, you have to just go to that address, and what the control signal is saying, you have to just perform that operation. Okay. And as I have told, that it follows the von Neumann architecture. It means both the instruction and data will be in this memory only. Both the instruction and data. Here there will be instruction also and data also. So first, write the heading memory organization. Draw this diagram. Now write few points. At the first point, memory is a storage element. Memory is a storage element. Memory is a storage element in the computer system. Memory is a storage element in the computer system used to used to store the user program used to store the user program. Memory is a storage element in the computer system used to store the user program. Okay. Now write the next point. Memory chip. Memory chip is divided into. Memory chip is divided into equal parts. Memory chip is divided into equal parts. Memory chip is divided into equal parts called as cells. Memory chip is divided into equal parts called as cells. Full stop. Full stop. Each cell is identified. Each cell is identified with a unique number. Each cell is identified with a unique number called as address. Called as address. Each cell is identified with a unique number called as address. Now at the next point, memory chip. Memory chip recognizes the control signals. Memory chip recognizes the control signals to indicate the type of operation. Memory chip recognizes the control signals to indicate the type of operation. Memory chip recognizes the control signals to indicate the type of operation. Now, whenever the CPU will generate a memory request, now next point, CPU generates the memory request. CPU generates the memory request. CPU generates the memory request to access the program. To access the program from the memory chip. CPU generates the memory request to access the program from the memory chip. From the memory chip. That is that is. So now we will see. There's a we are now will talk how the CPU generates the memory request. It will just give an address and also control signal. So this is the memory request that the CPU will generate to access the program from the memory chip. So this address, what it will do, it will enable the memory cell so that you can read or write at that location, at that cell. Enables the memory cell. Okay. And what does it do? It indicates the type of operation. Indicates the type of operation. This is the memory request that will be sent by the CPU to access the program from the memory chip. Okay, so just draw this diagram. Now we will understand the next important point regarding the memory. Now write the heading: memory chip configuration. Memory chip configuration. Now suppose we have a memory which is having four cells. Okay, these are the four cells. Now whether can anyone tell that how many bits are required to address these four cells? How many bits are required to address this four cell? This memory has been divided into four cells, and we have to give a unique number, a unique address to each of the cell. So what is the minimum number of bits required to address each cell? I'm waiting for the response from all of you, that if there are four cells in the memory, then how many bits are required to address these cells? So as we seen earlier also, that to address each cell, we will require only two bits, like for this cell 00, 01, 10, 1. So we require only two bits to address four cells. So if there are n cells, so we require log n base 2 bits. Very good, Rugved. Very good, David. Very good, Ritvik. Very good, Arpit. So for n cells, we require log n base 2 bits. Okay. Now write the heading memory chip configuration, and write a line under that. Write a line. Number of address bits, number of address bits required to access the memory, number of address bits required to access the memory is always depends on the capacity of a memory chip, is always depends on the capacity of a memory chip. Number of address bits required to access the memory is always depends on the capacity of a memory chip. Okay, full stop. Memory chip configuration is memory chip configuration is represented as memory chip configuration is represented as we will see now few configurations. Maybe somewhere I hope you all have seen written like this: 64K cross 8, one configuration; 64K cross 16, another configuration; 64K cross 32. This 64 can be anything, can be also 32K or anything. I've just taken an example. So if we take this part, suppose this configuration, now we'll try to understand what this configuration means. So whenever you talk about any memory, whenever you talk about any memory, you say that there are many cells in that memory. So this first part, it represents the number of cells in the chip, number of cells in the number of cells in the chip, and this part, it represents the cell size cell size, that what is the size of this cell, actual size, how much data can be stored in this cell, right? And it will be in bits. It means number of bits stored in the cell, stored in the cell. So you can say 8 means in each cell there will be 8 bits of data. Bits, always remember, in bits, 8 bits of data. And how many cells are there? 64K. K means 2 ki power 10. So for 64K cells, can you tell me how many number of address bits will be required? The number of cells are 64K and K means 2 ki power 10. Then how many number of address bits required? I'm waiting for the response from all of you. Number of address bits. This hash is number of, okay? Number of address bits required to access the chip equals to, it will be, I have already told, if there are n cells, then the number of bits will be log n base 2. So here are 64K cells. So the number of address bits will be log of 64K base 2. It will be 64K means K means 2 ki power 10. 64 means 2 ki power 6. So 2 ki power 10 plus 6 means 2 ki power 16. And log of 2 ki power 16 base 2 means 16 only. So the number of address bits required is 16. Okay. So if this configuration is given for any chip 64K cross 8, it means there are 64K cells. In each cell size is of 8 bits. Each cell size is of 8 bits. And to access any cell, the address size should be of 16 bits. Very good, all of you who have responded. So for each, if this configuration is given 64K cross 8, means each cell can store 8 bits. Very good, Rugved. Each cell can store 8 bits, and total number of cells are 64K, and to address any cell 16 bits are required. So whenever you get any configuration, you should be able to understand that what that configuration means. Okay, so these are the different configuration. What does this mean? That each cell can store 16 bits, means 2 bytes, and total number of cells are 64K, and to address any cell 16 bits are required. What does this mean? That each cell can store 32 bits. 32 bits means 4 bytes, and there are 64K cells in the memory. Each cell required to address 16 bits. Okay, now just write down this as an example in a notebook. Now I hope all of you have noted down. We will see few more examples of the configuration. In the exam, they ask the trick way. For example, suppose they have given like this: 1K cross 2. So 1K cross 2 means the number of address bits means 1K 2 to the power 10. So 10 bits address space, right? And in each cell there will be 2 bits. Always remember this is bits in bits, not bytes. This is in bits. So 2 bits data space. So in this way they ask the question: the address space and data space. So 10 bits address space and 2 bits data space. Now take another examples. Suppose they have written like this. The configuration is like this: 2 to the power m cross n. Then what will be the address space and data space? So you know that you have to take the log of this, then you will get the address space. The space will be m bits address space and in each space there will be n bits of data, n bits data space. Okay, let's see one more way. Suppose it is given like this, x cross y. The configuration is like this, x cross y. Then we know to get the address space we have to take log of this. So log x base 2, log x base 2 bits address space, and in each cell there will be y bits, right? So y bits data space. Just write down all these examples. This is the way to write the configuration and the generalized way. Okay. I hope all of you have noted down. Now we will see a practical example to understand it completely. Now suppose whenever you have to access any memory, that address is stored in a address register. Okay, and suppose the address is of 16 bits. Now suppose you have an address register which is of 16 bit. So this is 16-bit address register. Okay. Now what happened? These 16-bit address will be given to the address decoder, and we have seen the decoder functionalities. The input is of 16 bits, so output will be 2 to the power 16 signals, right? And it will enable one of those. So suppose this is D naught. They have started with 0, D naught, D1, D2. It will go up to D of 2 की power 16 minus 1. Total 2 की power 16 signals. And each signal, suppose this is a memory, okay? And suppose this memory is 64K cross 8, okay? Suppose this is one cell, this is second cell, 0, 1, 2, and then other cells, right? Each cell will be of 8 bits, 8 bits, right? This is cell 0, first is cell 0, this is cell 1, cell 2, right? And that way it will go up to cell 2 की power 16 minus 1, cell number. So now this will be associated with each cell, right? Now what will happen when a 16-bit address will be given, then the address decoder based on this address, right? Based on this address, it will just enable any one of these cells, right? Suppose if the 16 bits is all 0, then it will enable this first cell. If the 16-bit value is 1, then it will enable this cell 1. So based on the address value, this address decoder will enable one of these cell among the total 2 की power 16 cells. Okay. For example, suppose example, CPU generates the memory request, and we have seen in the memory request what does it contains. It contains the address and control signal. Suppose it has maintained the address in the form of hexadecimal code. So these are 16 bits. H means hexadecimal. So each part is represented using 4 bits, 4 zeros. Total 16 zeros are there in binary. But it has been written in hexadecimal. Hexadecimal means grouping of 4 zeros and ones. I hope it's clear. Everyone knows about the hexadecimal. And there is a control signal. If we write the, suppose the control signal will be, suppose read. This is the CPU. This is the memory record generated by the CPU. Now this value will go into the address register. From the address register, it will go to the address decoder. It will generate the decoding signal, and then it will enable the cell, enable that corresponding cell to which the address belongs to. So I hope now it will be clear to all of you that how any address will enable any cell of the memory. It will be done using the address decoder. Okay, so just draw this diagram. I hope this diagram will explain clearly to all of you that how the CPU generates the address of any memory and how the address decoder will active that cell. And when the cell will be enabled, then the data can be read from that memory cell. So I hope every these all things, these are the very basic things. We will go deep down in every concept, but these are very basic things that will build your concepts on the for the computer organization and architecture. So I hope what we have learned today is very well clear to all of you, or anyone has any doubt. If anyone has any doubt, you can ask. Okay, so I hope whatever we have learned today is very well clear to all of you. Okay, very good. So now I am ending the today's session. Just revise what we have learned today before coming to the next class. Okay. Okay, so bye. Good night, all of you.